Hello, everyone. I just finally finished recording that solution to the last problem we didn't get to work last time, where I basically had 4 liters of 98-degree tea that I was adding 2 kilogram block of ice to. I didn't work that problem, and I meant to set it up on my YouTube channel, and basically I kept running into the problem, so I didn't get it done until just a few minutes ago. As soon as class is over, I'm going to post that. So that's something you guys should look at just to help you learn how to do calorimetry problems. There's 2 ways you can do it. Generally, basically, people will say the summation of the change in, or the summation of the additions of heat, delta Q equals 0. And then you've got to, be very careful and make sure you make the right signs and everything. Or you can take all the things that are losing heat, add all them up and make sure all those quantities are positive, and then set that equal to all the things that are gaining heat, make sure all those quantities are positive, and set them each up equal to each other, and then solve for the unknown variable. That's the way I like to do it, just because sometimes when you're in the heat of a test or something like that, it gets a little confusing. Whether your heat of vaporization, your latent heat of vaporization, or your latent heat of fusion should be positive or negative. So in order to avoid all that, I just do it that way. But anyways, it's neither here nor there which one you want to do. But in that case, I did it that way, and I explained the other way. I did make one mistake in the process of recording it, but I caught it immediately. I used a 2 kilogram figure instead of a 4 kilogram figure. But I correct that in real time, so everything should be fine. Hopefully that'll help you guys. It also included a change of state, so that's another level of calorimetry problem that makes it a little more complicated. You should probably do something like it in lab as well. That'll help you. Does anybody have any questions on anything so far? Anything from the earlier parts of the semester or whatever? I'm just looking right now to see. We're in chapter 19, and chapter 20 I'm really covering really quite shortly. In other words, I'm pretty much just asking you to know your laws of, or excuse me, your second law of thermodynamics in many forms. I listed that last time as your goal that you need to do. So make sure you guys do that. Look in your textbook and maybe even look for other resources and look for various forms of the second law of thermodynamics. We are in the 14th week now. Next week will be the 15th, and then the following will be the final exam. We have had numerous practice tests. Our most recent test, in fact, is due on April 24th, which is a couple days from now. That's chapters 29, 30, and 31. We have since leaving chapter 31, we have went back and done chapters 17, 18, and 19, I want to say. Let me see, was it 17 or was it 16? Was it 18? Yes, it was 17, 18, and 19 will be the next test. And actually, that will include 20, where I ask you questions about the second law of thermodynamics. So I'll probably open that up. Heck, I'll open that up right now. Let me double check, make sure the questions are up to snuff. Sometimes when you open them up, the questions don't transfer in. I'm looking at it right now to make sure it does.
Professor Younger?
Yes, go for
it. For the practice test for that test, it only let me take one attempt on it.
Okay, that's weird. All right, let me, what's your name again?
Sean.
Okay.
Jolly.
Gotcha. I actually wasn't looking at the screen, so that's why I wasn't sure. I thought it was your voice, but I wasn't positive. So let me look at this now, and that's the practice test for test 6.
Yes.
Okay.
It was same for me.
Okay. Yeah, that's just a goober mistake on my part. Let me fix that real quick. It looks like the actual test is working. So that's good news. So test 6, I'm going to go ahead and open up right now, and I will give y'all until, let's say, Friday of next week to get that done. So let's say it'll be Friday 11:59 p.m. That's what I'll make as the due date, and that should give you ample time. Let me correct test 6 practice tests as well. Yep, it sure enough says 1 attempt, like a crackhead. Your instructor's such a goober. Allowed attempts 1. What the heck? So allow multiple attempts. And in fact, I want, whoa, Nelly, it's going really slow. Allow multiple attempts. Only the highest is kept. The time limit, how much is the time limit I've been putting on practice tests? Do you guys recall?
There was no time limit.
There hasn't been in the past though, or has there been in the past? I thought I
think it's 20 minutes.
20 minutes. Okay, I'll put that. This just because I give some extra credit for you guys being able to do that in the allowed time. Get rid of this part. Okay, it looks like everything is up now. And okay, so you now have unlimited attempts. I'm sorry about that. That's been corrected. Let me go back now to the actual test, which as I said was actually working. So I'm going to open that up and have a due date of 11:59 p.m. Friday, which will be a week from tomorrow's Thursday. That'd be 22nd, 23rd. So that'd be the 30th. 30 days, that's September, April, June. Yep, 30, that'd be April. So we're golden on that one. And here we go. So I'm going to open test 6. Sorry for the narration, it just keeps my Alzheimer brain working. So time limit for that one's 31 minutes. And I'm saying it will be due on I'm going to say it's due on Friday the 30th at 11:59 p.m. And now it should be saved and published and all that good stuff. I gave you 4 attempts, even though it says 3. I'll leave it at that. So you guys, it says 3. It'll tell you can take 4. So I'll let you have 4. I don't care. All right. sorry about that. I'm so strict. I'm such a disciplinarian. All right. Does anybody else have any other questions? Corey Carr fixed the issue that you had asked me about last time, but I literally didn't do it until a couple minutes ago. I did it a weird way than that I was advised to, so I'm curious to see if it works. It might only let you do it once. If that's the case, email me and let me know. I don't even know if Corey's here. Yeah, she is. Okay, she or he, not really sure. Anyways, yeah, that's taken care of too. That test 2 thing is done. The other students are not in this class, so good. Thanks, Corey. All right, so we've now done basically most of the stuff for chapters 17, 18, and 19. Chapter 19, in fact, we stopped at calorimetry. And what I was telling you just now is that when you're actually doing calorimetry experiments, what you normally have, if you're actually doing it in the lab, what we have is a little calorimeter cup. And the calorimeter cup basically is a aluminum cup like this that's made of aluminum. And it's got this little lip that sticks out like this and then comes back in like so. And that little lip allows us to put a little wafer in it. And that little wafer is cardboard. You know, something that's really a good insulator, in other words. And then that allows it not to touch the aluminum outer cup, and it gives it a little air. And then you stick inside of it yet another aluminum cup that just fits inside of there like this. And in there you can put, for instance, water, and you have a little thermometer, say, going up and out. And there's even a lid that you can put on this with a hole in it. and then the thermometer sticks out so you can read it. By doing this, basically you've isolated the system to include the water and this little inner aluminum cup. That little aluminum cup you actually know the weight of, and if you leave this water in it with the thermometer long enough that the thermometer starts moving, then you can reach the conclusion that the aluminum cup and the water are actually at the exact same temperature. So you, in fact, even though it's really hard to take the temperature of solid aluminum, you can assume the solid aluminum has the same initial temperature of the water. Then you can take, say, a little sample of metal like this with a little ring on it, say, and that little sample of metal can be lowered into a vat of water that's boiling. If you, since it's a metal, it's a conductor, so it actually maintains or gains the heat of the surroundings rather quickly. So if you leave it submerged in boiling hot water for 5 or 6 minutes, then this thing will have an initial temperature of 100 degrees Celsius. Of course, you could also correct for that because low atmospheric pressure might allow it to be at, say, 99.4 degrees Celsius, or high atmospheric pressure might not allow the boiling to occur until 101.6 degrees Celsius, something like that. But you'd have a thermometer in that to actually check to make sure that temperature is what it is. So what you do is you'd set this long away from the heating source, of course, and let it reach equilibrium so the thermometer stops moving. Then you know the initial temperature of this, and let's say that initial temperature is like 22.0 degrees Celsius. That means the temperature of the water and the temperature of the aluminum cup are both 22.0 degrees Celsius. Now you have left this sitting in here for a whole 5 minutes, so you can be pretty confident that this piece of aluminum or tin or steel or zinc or whatever, you can be pretty sure it's going to be that 100.0 degrees Celsius, which is what we'll assume. Like I said, you could still correct for it not being that just by taking the temperature. And you're going to take that and put it inside of that liquid container of liquid water. And then you're going to take and stir it up and allow that container of water to reach equilibrium again with the new metal that's in there. So the new metal is in there like this, and it now reaches a new equilibrium temperature. And let's say the temperature, anybody want to take a guess what that temperature might be? Let's say this thing is about 40 grams and this water is about 60 grams of water. This is 100 degrees Celsius. This is 22 degrees Celsius. What do you think the final temperature approximately will be of the water after it's reached equilibrium and cooled the metal down from 100 degrees Celsius? Anybody have an idea? Would it be about 22, or would it be about 100, or would it be dead center between them, or a little closer to, a little further away than 22, but not quite, midway, or a little closer to 100, but not quite midway? What do y'all think? Someone thinks they're disgusted with me.
Closer to 22?
Yeah, it is. That's sort of the key point is, and that's what I was telling you about water having such a large specific heat. It takes a lot of heat to make water change its temperature. So when you actually do this experiment, it's not uncommon for this water to go from 22 to 24.1 degrees Celsius. In fact, that's a little bit too big. It's usually less than 2 degrees Celsius temperature change. So that's indicative of how much specific heat water has. So when you do that experiment, you actually have a nice way of working calorimetry. You can say delta Q equals 0. And what you're just saying is some of these things will have delta Q equal negative. Some things will be delta Q being positive, but the sum of all of them should be 0 because we're assuming this calorimeter is pretty close to exact. And it really is. I mean, what you've done by putting this little wafer here is you've prevented conduction from taking place between the inner aluminum cup and the outer aluminum cup. And you've gotten rid of the ability to do convection because you actually have air trapped between the two. So you can't do conduction, and you also can't really allow much airflow within. So you're getting rid of really all the ways that heat could be transferred from this inner cup to the outer cup. And instead of trying to isolate the system from the inner cup, you actually weigh the inner cup, make sure it reaches equilibrium, and then you get basically the system as a whole having a net Q equal to 0. So what you do is you'd say, okay, well, the Q's that we have, Q are MC delta T. That's for whenever something changes temperature. If something changes state, its Q is equal to ML, where L is a latent heat of fusion. That's in going from a liquid to a solid or a solid to a liquid. And one way is positive, the other way is negative. Or vaporization. Again, that's going from liquid to a gas, or gas to a liquid, one way being positive, the other way being negative. Or sublimation, where it can literally jump from solid state to a gaseous state like carbon dioxide dry ice does. Okay, so those are the ways you can actually change heat. So what you can do with this is you can say, okay, well, the water is actually going to have an initial mass, H2O. It's going to have a specific heat of water, H2O, and it's going to change temperatures. And in fact, the final temperature is going to be larger than the initial. But by using this delta Q, I don't have to think about that at all. By using delta Q equals 0, I just have to remember to use delta being final minus initial. So I'll say T final minus T initial, and I'm going to say this is H2O. Okay, this T final is the total final temperature of everything, so I don't need another subscript. This is T initial for the metal. So that's the MC delta T for the water. Well, it turns out there's also, plus, there's also a MC delta T for the aluminum cup. So I'll put M of aluminum, meaning the inner aluminum cup here, C aluminum, again, specific heat for aluminum. And just like the water, its initial temperature would be about 22 and its final temperature is going to be higher. So again, I'll say T final minus T. And since we allowed the water and the thermometer and the aluminum cup to sit there long enough for the thermometer to stop moving, then we know the aluminum's actually reached equilibrium with the water. So I'm using the initial temperature of the water because that should be the same as the initial temperature of the cup. Okay, so that's two parts of the system, the water and the cup. Now you're taking this hot object, this hot metal, and you're dumping it inside there. So there's another MC delta T that's going to happen. This is the M of the metal. So whatever mass that metal had, the C for the metal, which is what we're looking for. So in the lab that we normally do, you're actually solving for this. And then you're going to multiply it by the final temperature minus the initial temperature. Now, the final temperature in this case is actually going to be lower. The initial temperature is going to be like 100, but the final temperature is going to be like 24 or something like that. But you still, because I use delta Q equals 0, I still do T final minus T initial. So I'll say T final, which is the final temperature of everything. That's the whole point of this experiment. Once you lower the metal in there, and you start to stir it up, and then you reading this thermometer, you're watching the thermometer go up, 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 and then it's going to sit still for an extended period of time. And if it sits there long enough, you can go ahead and conclude that it's reached its max temperature. If you watch longer, it'll start to cool off again because now it's hotter than the room, so it's giving off energy to the room. But that'll be the final temperature, and it's the same for both the water, the cup, and the sample. So it'll be just plain T final minus, in this case, T initial for the metal. So you now know all these quantities. You know the mass of the water because you weighed the cup before you put the water in it, and then you weighed the cup after you put the water in it. You subtract the two, that would give you the mass of the water. You know the specific heat of water is 1 calorie per gram per Celsius degree. You know the initial temperature of the water is 22.0. You know the mass of the aluminum cup because that was the first thing you measured. Remember, you did the mass of the aluminum cup and then the mass of the aluminum cup with water in it, and you subtracted it. Well, the mass of the aluminum cup, so it goes here. You look up the specific heat for aluminum, and that'd be like 0.073 or something like that. The T final again is what you're actually going to put in from your experiment, and the T initial is again that 22 degrees Celsius, and then plus the mass of the metal, which you weighed before you stuck it in the boiling hot water. The specific heat of the metal is what you don't know, so you're going to solve for that. And then again, TF and TI metal are things that you're actually going to know. The TI metal is the 100.0 degrees Celsius, and the T final is just that 24.1. Obviously, you can, since all of this is equal to 0, you can take this term and this term, put it over there. They're going to become negative. And then you're going to divide by the mass of the metal and divide by the difference in temperature here, and that'll give you the specific heat of the sample. So that's how calorimetry is done. Normally, that's a really nice experiment. You get to see real physical things happening. You can make sense of why, you know, so many dishes that you cook call on you to bring water to a boil and then put stuff in it, so on and so forth, especially regarding meats and other things that could get you sick if you don't cook them properly. So it's really a good lab. We don't do it right now because we're in, you know, quarantine or whatever, but we do something like it in some of our labs. So hopefully y'all have something like this in a lab simulation. But I just wanted to show you that's really what calorimetry does. Specific heat, remember, is those slopes. When I showed you how a particular substance, we were working with water, had a very steep slope, and then it leveled off. This was heat added basically versus temperature. And basically as a solid, it was steep, and then it reached 0 degrees Celsius. And then for water, then it leveled off for a long time until enough heat was added for it to actually completely melt. Then the temperature would go up again and again and again until it reached that 100 degrees Celsius where it would boil. It would stay that temperature for a long time until enough energy was put in to melt, to boil all the water away. And then in fact, we get another specific heat there. So these are specific heats, these slopes, let's say 1, 2, and 3 for the different states. And then these energies from here to here are latent, in this case, heat of vaporization, and in this case, the latent heat of fusion. So that's really, you know, how we take into account each of these things. If you actually have to go across the state, then you're going to have to add another term in here. In other words, if one of these substances is going to change states of matter from solid to liquid, or liquid to gas, or liquid to solid, or gas to liquid, any of that kind of stuff, then you're going to have to take that into account. And what you got to realize is in going from a solid to a liquid, heat must be added. And in going from a liquid to a gas, his heat must be added. But going the opposite way, heat must be taken away. So the Q's are negative. Okay. So that should give you all you need to know to solve other calorimetry problems like you'll see in section 19.4 and various homework problems, as well as things at the end of the chapter. Remember, guys, if y'all are having problems with homework problems, look for ones like it at the end of the chapter, specifically odd ones, and then try to solve those. Check your answer. If your answer matches that one, you can be pretty confident that you got it right, and then you're in a better place to solve the problem. So, any questions on that, folks? Okay, so we've covered chapter 19 in terms of basically knowing the mechanical and thermal equivalents of energy, of heat. There is a mechanical energy that we used to measure in joules, and then there's a thermal energy that we measured in calories. And Joule did that experiment. Joule did that experiment that showed us that 1 calorie was 4.186 joules, or 1 kilocalorie is 4,186 joules, or 4.186 kilojoules. Now we've got to go on and discuss, in terms of like ideal gases and things of that sort, what is the internal energy? So when I talk about internal energy, your book is using the symbol E. Okay, some books use U, all sorts of stuff like that, but your book is using E. So internal energy really is the energy the molecules and atoms have as a result of, say, their temperature. And in fact, for an ideal gas, the internal energy, E internal, is equal to the number of molecules you have times their average kinetic energy, which is 1/2 mv squared average. Okay, notice I'm doing the total V here. I'm not doing Vx, Vy, or Vz. So in fact, that turns out to be, since kinetic energy is 1/2 mv squared, which is 3/2 kT, you can say this is actually going to be equal to 3/2 N kT, and that's the internal energy of an ideal gas. Evidently, the internal energy of an ideal gas only depends on the temperature and the number of actual atoms or molecules in it. Okay, the 3/2 represents its 3 degrees of freedom, and that means translational degrees of freedom. So left, right, in, out, and up, down, right? Things like vibrating, that's not one of those. Things like spinning about one axis, meaning 2 atoms are here and they form sort of an axis of rotation, and a third atom's out here orbiting around it. That's another degree of freedom that we're not taking into account here. This internal energy is really the one that's connected to temperature. You can also, since we know the relationship between the Boltzmann constant and the ideal gas constant, then we can also say this is 3/2 lowercase n r t, because remember, Boltzmann constant and Avogadro's number are related to the ideal gas constant. So that's the internal energy of an ideal gas, written 2 different ways. And this helps you, like when you start to think that specific heat is really the heat that must be absorbed to make the temperature go up. Well, when you're talking about water, the temperature only goes up as a result of these 3. The molecules speeding up from left to right, the molecules speeding up in and out, and the molecules speeding up and down. But water, since it's this molecule that looks like this, like Mickey Mouse, okay, water can actually speed up such a way that this and this vibrate more, this and this vibrate more. No problem, Corey. And it could rotate about this axis, and it could rotate about this axis. Okay, it could also rotate about an axis through the center here. So all those different degrees of freedom are other ways that you can add heat to water without it raising the temperature, because to raise the temperature, you can only apportion a part of what heat's added to these 3 degrees of freedom. And the Equipotential Theorem says that basically if you've got 7 degrees of freedom, we've got 3 here plus 1, 2, 3, 4, 4 here. So that gives you about 7 degrees of freedom. When you got 7 degrees of freedom, each one gets an equal part of the energy. That's the Equipotential Theorem. So 4 of the 7 go to making it do things other than heat up, and the other 3 make it heat up. That's why the specific heat of water is so high. That's why, for instance, Great Britain has a climate that's more like, let's say, Virginia and Maryland, even though it's lined up with like southern Canada, all because of the specific heat of water. That's also why we get, things like the water having a nice cool sea breeze and also stuff like that. So the specific heat of water is a really big deal. It affects us more than you know. Now, to go on, what we need to do is think about the first law of thermodynamics, which I sort of been hinting at anyways. The first law of thermodynamics really is about energy being conserved. So the original idea was energy is neither created nor destroyed. And I want to say it was Joseph Priestley who did the experiment. I could be misremembering that because this is from like middle school that I remembered. But basically he burned a bunch of things, weighed everything before he burned them, and then captured all the debris that fell off of the fire and weighed that and found that the masses of everything combined was about the same. And therefore he concluded that mass conservation was a thing as well. Well, he's right as long as you're, measuring only to, let's say even 6 decimal places. But once you start to get to the, let's say 16th decimal place and stuff like that, it turns out he's wrong. What really is conserved is mass energy. So that's after relativity, we had to reach the conclusion that mass energy is what's conserved, because if you actually took the energy, the heat that was put out by that fire that Mr. Priestley made, if you took that energy and divided it by c squared from the famous E equals mc squared equation, then you would actually find the amount of mass that was lost. Only his experiments couldn't detect it, because as you can tell, you're going to take an energy, which might be pretty significant, but you're going to divide it by 9 followed by 16 decimal places. Okay, so the mass would be really, those mass change would be small. So for all intents and purposes, we can still pretend in everyday life that the total energy is conserved and that the total mass is conserved separately. But once we start getting into where a buttload of energy is put out comparable to E equals mc squared, where m is the mass, then we got to reckon with that. So that brings us to our new version of this first law of thermodynamics, and that's this new version, which looks different, by the way, from the version that you'd see in chemistry. They basically would say that D internal energy, so this is a change in internal energy, is equal to the heat added minus the work done. Okay, now it's often pedants like me, teachers and whatnot, pain in the butt people, academics, will put a little bar on here, and I want to, and I'm going to specifically because I can't not do it. When you have a DE, that means you should be able to integrate it and get an E, and that's true for internal energy. That is not true for Q, and that is not true for W. In the words of differential equations, these are not exact differentials. For instance, you can't say Q is a function of X and Y so that dQ is equal to the partial of Q with respect to X dx plus the partial of Q with respect to Y dy. If you could say that, then it'd be perfectly fine to write this as dQ. Same thing with work. But it's not an exact differential. In fact, the way you go from one state to another really matters. So you can't just say this. So I will continue to put it this way. But the big thing to realize is that the change in internal energy of a system is equal to the heat you add to the system minus the work done by the system. So this is work. Well, I don't know why I started with that would be. Work done by the system. Okay, so whatever system you're studying, the system that has an internal energy E internal, okay, that is the work. If you calculate the work done by it, not on it, then you have to have this minus here, and this is heat added to the system. So I'll just say heat added. So the internal energy, if you add heat to it, yeah, it's going to go up, because where else is the heat going to go to? If you have the system do work, maybe it's the system is a little bit of gas inside of a piston, inside of a cylinder, right? If you actually apply heat to that cylinder, the ideal gas law tells us that that gas in that cylinder is going to increase in pressure and temperature. And then that's going to, because the pressure increases, that's going to push the actual cylinder lid up a little bit and be, in fact, doing work. Well, that work that's done is actually taking away from some of the internal energy that could have been increased. So that's why we put the minus. If you're doing this in chemistry class, they do not the work done by the system. They talk about the work done on the system, and they use a plus dW. So if you're taking chemistry right now, this can be confusing. That's why I'm taking the time to point out the difference between this version and the version that they use in chemistry. So we use D internal equals the heat added minus the work done. And I don't even remember it. I just always, when I get to the new thing, I work it out, look whether there's a sign, a minus or not, and make sense in my head whether that has to be work done by the system or on the system. And obviously, if I had a plus there, that would be work done on the system, because if I actually compress the gas, I'd be doing work on it. That would actually cause an increase in temperature and internal energy. So I know the positive would reflect work done on instead of by. So that's the first law of thermodynamics. And in fact, if you take a engineering thermo or an actual thermodynamics course in the physics department, a lot of your life will revolve around taking this little differential and substituting things for dq and dw and de and all this good stuff, and using thermodynamics square, which gives you all these different energy functions like the Gibbs free energy or the entropy or the enthalpy and all this stuff. We're not going that deep. You don't need to go that deep, but I want to talk to you about some processes that happen. I'm trying to give you the rundown of the actual material, and then I think the material itself is easy enough to solve the problems once you know the fundamental idea. So the first law of thermodynamics really could be extended by saying this, but it also could be extended because you've got to take into account that what about mechanical energy? Well, then you're going to have to say, well, okay, well, the change in kinetic energy plus the change in potential energy plus the change in internal energy, well, that's going to be equal to the heat added minus the work done. Okay. So both of these are versions of the first law of thermodynamics, but this is one that's sort of narrowed down for you just talking about thermal energy and work, not specifically macroscopic mechanical energy like individual particles moving with velocity v, so that their kinetic energy is 1/2 mv squared, and above the surface of the earth, so their potential energy is mgh. So this is the more general form. The main thing is you guys got to remember this expression for E internal and this expression for E internal, and I keep writing the I, the NT without the I, okay? And then you need to know this version and this version along with what this work done by means and what this heat added means, okay? The rest of thermodynamics really is about a lot of terminology. There's a lot of terminology that exists, and if you don't know it, you can't solve problems. One case in point is called isothermal. So isothermal processes. Isothermal process means delta T equals 0. So when something's said to be isothermal, that means it has no change in temperature. Can you tell which, if any of these three things is going to be 0? And you can even assume it's an ideal gas if you want. Anyone?
The E internal.
Exactly. Because, as we said, an ideal gas's internal energy is N times the average kinetic energy, translational kinetic energy of the molecules, and that equals 3/2 kT or 3/2 nRT. Then by that, we know that's the internal energy, and it only depends on the temperature. So if the thermal, if it's isothermal, the T can't change, therefore the D internal can't change. So now all of a sudden you've got, oh, wow, the heat added must be equal to the work done by the system. So in other words, if you set up that cylinder with gas inside of it and a little piston head on top of it, and you add heat to it, if you have some little gremlins in there whose job is to work infinitely hard just to maintain the temperature not changing, and they're in tune with everything, then what they're going to do is rapidly move the piston head up and down as much as they can to prevent the temperature from going up or going down. And what would result is every bit of heat added going into the PDV happening. So remember, work is equal to the integral of F dot dl, which if you see F as equal to pressure times area, and then dl would be the distance, you could see that this is pressure times A times dl, which would be integral of P dV. So pressure integrated over dV would give you the actual work. So what's happening is the cylinder, which might have been shaped like that before, now has the piston head moved up a ways like this. And this amount of work done, which is the integral of PdV, is equal to the heat added. So that's what an isothermal process results in. There's another process called adiabatic. And for an adiabatic process, that's one that's either so perfectly insulated that delta Q is equal to 0, or it happens so rapidly that the slow, cumbersome process of conduction can't take place. So the main thing is dQ is equal to 0. So in the first law of thermodynamics in this form, every bit of internal energy change is going to come from the negative work being done by the system. In other words, negative work being done by the system means work done on the system. So the only way you're going to change the internal energy is by doing work on the system. So that's an adiabatic process. There's also an isobaric process, which if you remember, bars are units of pressure. You might realize that this is delta P is equal to 0. So in PV equals nRT, you can see when P stays a constant, then what that means is if you solve for P, you get nRT over V. If the temperature goes up, say, then the volume is going to have to go up by an equal amount to maintain that constant pressure. So that's isobaric. There's isovolumic, which is also isochoric, if I remember correctly. Isovolumetric, which I think you can guess just from that name that means delta V is equal to 0. Obviously, in that case, then at least for as far as gases go, you can't have any work done because the integral of PdV, if there's no change in V, then there's not going to be any work done. So that's a ramification of that. And you could also, by the way, they do call, if I remember correctly, isovolumetric is also called isochoric. So that's another process. So with all those processes, you can reach cool conclusions like isobaric process, for instance. That means work is just equal to P times delta V, because you're going to integrate a constant P. That's going to come out in front, and I just get the integral of dV, which is just a volume change. If I do isovolumetric, then, like I said, work is equal to 0. If I do adiabatic, then dE internal is equal to negative dW. So again, it's the negative of what work is done by the system. So all of those give you different things. If you actually do, let's say, work done in an isobaric situation, work equals P delta V, then you could actually say, okay, well, the P could actually equal some P as a constant, and then the delta V would actually be like nRT over actually just nRT over P, right? So you could actually use the ideal gas law to put that in there as well. Does somebody have a question? Sorry, I lost my train of thought too in the middle of that. Someone have a question? Okay. The other thing to remember is with this ideal gas law, this is really the ideal gas law. And as long as you know the number of moles, the ideal gas constant, the T, and one other variable, in other words, you know all the variables but one, you can solve for the other variable. but it also allows us yet another version, which is P1 V1 over T1 is equal to P2 V2 over T2. So that's another version of the equation you can use. And you just got to remember, you can use any units you want for pressure and volume, but the temperature's got to be in Kelvin. So T must be in Kelvin. Okay, if it's not in Kelvin, you'll have problems. But everything else can be the same because it's just going to be a simple ratio. Remember, the way you convert, say, from Celsius to Kelvin is an additive thing, not a multiplicative thing. So, you know, adding to something down here without adding to here would definitely make the equation no longer valid. So that's really the big picture on how to use the ideal gas law. Now, when you go to use the ideal gas law, there's other things we can actually find. You can find, for instance, and I'm not going to do the derivation. I just want to let you know what's important. What we know, for instance, is that Q, as we said before, was equal to MC delta T, and Q was equal to ML, where ML was heat of fusion, heat of vaporization, or heat of sublimation. All those are valid. But it turns out, if you want to talk about the molar specific heat, then you can also say Q is equal to N, the number of moles, times the specific heat times delta T. But here's the weird part. And you can sort of think of it in terms of with this thing right here. If you keep it a constant volume, then you know work has to be 0. So keeping it a constant volume, every bit of heat you add goes directly to the internal energy and therefore can change the temperature quite easily. Whereas if you do it at constant pressure, then some of the energy can go into work and some of it can go into internal energy. So you get entirely different values. So there turns out to be an NCV delta T, and there turns out to be an NCP delta T that are quite different. Okay. And specifically, basically CV is given by the molecular weight times the specific heat in lowercase units. So M times lowercase CV, and CP is equal to big M times lowercase CP. Okay. So those are two typical things we use. And the reason why we use that is because it turns out when you start to study an adiabatic process, then you can work out, and your book does this derivation, it's kind of fun, but what you'll ultimately work out is that CP minus CV has a very specific value. CP minus CV is actually equal to R. And from that, you can see, look, if I go ahead and solve for CP, you can see CP is actually equal to CV plus R, which goes back to what I was telling you. Remember, DE internal is equal to D bar Q minus D bar W. So when we're talking about constant volume, that must be, in fact, the quantity where every bit of heat goes into increasing the internal energy. Whereas at constant pressure, some of the heat can actually go into heating up or changing the temperature, but some can go to work. So you'd expect the specific heat at constant pressure to be larger than the specific heat at volume, because it could absorb more energy before changing temperature. So this formula gives us exactly that representation. So from a physics standpoint, it makes it make a lot of sense to me. When you go and work out the details of ideal gases, what you can find out is, in fact, that CV is actually equal to about 3/2 R. So you can say something minus 3/2 R is equal to R. So I could add 3/2 to both sides. That'd be 2/2 plus 3/2, that'd be 5/2. So that tells you CP must be 5/2 R. And you'd be exactly right. And in fact, if you look at the data, which is expressed in table 19.4, and that's on page 511, you will see that the actual results, experimental results, are pretty close. For instance, the accepted value of CV is 2.98 and CP is 4.97 for monatomic gases. If you look for diatomic, it becomes 4.96 and 6.95, but basically it matches the data pretty well. And this is all just from, analyzing ideal gases. Now, there's one other thing I'm really trying to get you to here, and that's basically this ultimate result, which is we already know for an ideal gas, P1 V1 over T1 is equal to a constant. So we can say it's equal to P2 V2 over T2. Now, if you have the temperature's not changing, then you can just leave those off and you have that equation. If you have the volumes not changing, then you can leave that and that off and you have that equation. Or if you have the pressures not changing, then you can leave that and that off, and that works fine. So all those individual sub-equations work as well. But the neat thing is, in your book in section 19.9, in section 19-9, it actually does a derivation for adiabatic processes. And what we find is in adiabatic processes, where basically dq is equal to 0, it turns out that you get this nice little dp over p plus plus gamma dv over v is actually equal to 0. And where gamma is defined to be Cp over Cv, when you do that, then lo and behold, there's a new equation that comes into play, and that is pressure times volume to the gamma power is equal to a constant. So you can say P1 V1 to the gamma power is equal to P2 V2 to the gamma power. That's a whole different equation than P1 V1 equals P2 V2. Okay, but this is only true for adiabatic processes, and I think it's also for quasi-static, meaning it has to be a process that goes very slowly. So it's for adiabatic quasi-static, meaning goes really slow processes. Another word for that is basically every stage is like an equilibrium state, so you can easily go from one state backwards or forward and still get the same thing. That's sort of an ideal idea, like a reversible process. So those are the equations from about ideal gases that I want you to be able to use, and I think you can see from the examples in the book this is pretty straightforward. I don't need you to be able to derive these things. I just need you to be able to use them just like the examples in the book, and I won't go much more difficult than the examples in the book, and nowhere near as difficult as the homework problems, at least not on a test. Now, other than that, all I want you to get from this chapter is basically the conduction, convection, and radiation. So it turns out when, let me turn this back to me, okay. So it turns out when you actually have something hot, the second law of thermodynamics says a hot object, an object with a high temperature, is going to basically let heat leave to go from that hot object to a cold object. That is the second law of thermodynamics. Heat by itself will flow from a warm object to a cold object that happens to be in thermal contact with. And thermal contact could mean physically, like I've got Raynaud's, so one hand is sometimes cold and the other one's warm. So if I take my two hands and put them together like this, right now my right hand is hot and my left hand's a little cold. I can actually feel that. And what is going on is the warm hand has a higher temperature. So the second law of thermodynamics says on its own, heat will leave this hot hand and go into this cold hand. Now you can force heat to leave the cold hand and go into the warm hand easily enough. You can actually take air outside, which is super cold in the winter, and you can pull heat from that super cold outdoor winter cold and put it into the warm space that's in your living room and your kitchen and your bedrooms, and that's called a heater. And the way you can do that is by paying a lot of money. So basically, yeah, there are machines that can make cold or make heat flow from a cold object to a hot object, but you're going to lose a lot of energy in that process. And that's why, you know, power bills go up and stuff like that. Similarly, you can also take air from inside of a cold refrigerator, cold air, and you can force it into a warm kitchen. And that's exactly what a refrigerator does. Again, you are paying for that. But if you just left it of its own devices, then the heat in the kitchen would actually infiltrate the actual refrigerator innards and make the refrigerator warm up. That's the second law. That's one of the many versions of the second law of thermodynamics. Now, how is this thermal contact done? Well, thermal contact means you could literally be touching, in which case that mechanism is called, anybody know what that type of heat transfer is called when the two objects are touching? It's the same thing for electricity. I suspect you are just not answering because I know you know. It's conduction, okay? So that's one way of heat transfer, and that's an equation that I want you guys to know. Specifically, actually, I'll write that in a second. So conduction does actually take place. Heat flows over a certain amount of time from a hot object to a cold object, and the amount of heat flowing per unit time is directly proportional to the difference in the temperatures. So like if my right hand is 103 and my left hand is 98, then that's a pretty good temperature differential. Whereas if my right hand is 98.6 and my left hand is 98.0, that's not a very big temperature. So that'll take longer for the heat to flow. So the amount of heat flowing per unit time is directly proportional to the difference in temperatures. It's also directly proportional to how big of an area that heat is allowed to flow through. So if I just barely let the itty bitty tips of my finger touch each other, that itty bitty cross-sectional area where the two pieces of skin are touching each other is very small, so very little heat will flow. However, if I do this, now I've gotten the area as big as my fingerprints. If I do this, now I've gotten the area as big as the surface area of my smushed finger. If I do this, now I've got it for my whole hand. So that heat flow per unit time, that joules per second or calories per second, is also proportional to that area of contact. And I literally mean area, like square meters, square centimeters. And then finally, if, let's say my finger had a protrusion, let's say it had like a wart or something, a really long, ugly, skinny wart, okay? Now, in that case, my skin of this finger would be touching my skin of this finger through this long wart that to the untrained eye looks like a pin, okay? Now that long wart being so long is a problem. It's going to take more time for heat to flow from this finger's core to this finger. And that says that the amount of energy flowing per time, the calories per second or the joules per second, is inversely proportional to the separation between them. That's really how conduction works, okay? There's also convection, which you've probably seen convection ovens and heard of them, where they can, you know, cook your baked potato in like 10 minutes instead of the hour or whatever. And what happens with that is it's easiest understood like in water. You can take a hot chunk of metal or some metal that's got current running through it, like the elements in your hot water heater, and you jab that underwater safely, of course, because, you know, there is some chance you get the crap kicked out of you by electricity flowing through the water and into you. But you put that hot probe of metal down there, that hot probe of metal heats up the water immediately around the probe of metal, the element, the heating element. That causes the molecules of the water around it to separate further and further apart because they're vibrating more rapidly. That makes the water in that little cell around the metal less dense, therefore it floats up. that lower density causes it to float up. And as it floats up, of course, it's actually going to expand even more, but eventually it'll get to the top. It'll release some of its heat to something colder, say the air above, and then it reaches equilibrium temperature with the water around it and falls back down, only to be replacing later some other water that has just left that heating element. That's convection. So building those cycles of heat, picking up heat, carrying heat up, delivering it, dropping back down, picking up more heat, that's convection. And then the third way is radiation, and we thought that such radiation could only travel through matter, but we've since discovered that it doesn't. That matter, it doesn't have to have matter for radiation to travel, say, from the sun to here, which is a good thing because there's almost no matter between us and the sun. So the energy that comes from our sun gets to us by radiation. And the law that dictates how that moves is called the Stephon Boltzmann Law. And basically, the Stephon Boltzmann Law, which your book covers, says that the amount of heat applied per unit time is directly proportional to some constants, the Stefan Boltzmann constant, the emissivity, which is a measure of how reflective or absorptive the material is, and the surface area. So it's directly proportional to surface area. So if you have, for instance, a burner that's this big on your stove, and it reaches the same temperature as a burner that's this big on your stove, then this little one can't put out as much heat per unit time as this big one can. So if you have a pot of spaghetti that's this big around and you need it to bring the water to a boil so that you can boil that spaghetti, then even though they reach the same temperature, you do not want to put that big pot of spaghetti on the little boiler. You want to put it on the big boiler or the big burner because it can actually produce more heat per unit time because of its large surface area. So the amount of heat, the calories per second, is directly proportional to the area that's putting out the heat. This is actually why men tend to hold on to their body heat a little better when scuba diving than women do when they're scuba diving. Women generally have a little bit more surface area due to curves and whatnot. And that larger surface area means more energy is distributed to the environment per unit time than to the environment by us. So delta Q over delta T for a woman is larger underwater than it is for a man. Now, the other thing it depends on, and this is kind of weird, but the other thing it depends on, it's not weird because it's temperature. Obviously, a 500-degree burner is not nearly as effective as a 700-degree burner if they have the same surface area, right? So it makes perfect sense that a 700-degree burner is more effective at producing calories per second than a 500 degree. But the thing that's weird about it is it goes like temperature to the fourth power. So if I double the temperature of my burner, let's say I make it go from a 500-degree burner to a 1,000-degree burner, then I actually increase the energy output in calories per second, not by a factor of 2, not by a factor of 4, which would be 2 squared, not by a factor of 8, which would be 2 cubed, but in fact, by a factor of 16. I'm trying to find a bunch of extra fingers to show you 16, right? So yeah, by a factor of 16 is how much the heat transfer would go up by on radiation. So that's really the end of this chapter. Let me show you those equations now real quick. So what I just said was the conduction equation says that the amount of energy delivered per unit time, so that's delta Q over delta little t. No, that's a little t. Notice that's a little t for, dang it, y'all can't see it. Notice that's a little t for time. Well, that turns out to be equal to some constant that is basically a constant related to the material you're actually dealing with, times the surface area A, times the difference in temperature, which would be T1 minus T2, over the length. So what I'm picturing here is a heat reservoir, if you will. And by that, I mean infinite source of heat that no matter how much heat I'm going to take away from it, it's still going to maintain that same temperature, T1. And then I have, for instance, a little tube of that material of constant K, which has a cross-sectional area A. On the other end of that cylinder, in fact, there is another heat reservoir and that heat reservoir has a temperature T2. This distance from here to here is L, and of course that surface area, which is the same as that surface area, is A. So it turns out that the heat transferred from reservoir 1 to reservoir 2 is the difference in temperatures times the cross-sectional area, and it's inversely related to the length L, but it's also related to the conductivity, which is what this number is, conductivity of the material that spans the two reservoirs. So this material right here is what we're talking about. Now, you might know from everyday life, like if you've ever worked construction or even helped your dad or mom or whoever insulate a shed, you might know of R values for insulation. So there's, for instance, R13 and there's R19 is the new two typical things you run into. And R19 is really supposed to be for 2x6 walls. And this is supposed to be for 2x4 walls. Now, often people will say, oh, okay, well, if this is R19, I will really save a lot of money by stuffing this R19 in my 2x4 wall. And they'll actually just be wasting a ton of money. And in fact, get worse results than if they used R13. Because the reason R19 is good is because of this L being so thick. And this L being so thick is partly due to air trapped in it. And air is really the good insulator there, better so than the fiberglass that the insulation is made out of. So when you actually force an R19 to be compressed into a 2x4 wall space, you're actually going to get an R value that's actually less than 13. And 13 is the minimum that code requires. So your building inspector, if he notices it, would actually fail an inspection. So don't do that. But that R value might automatically say to you, well, what is this R value? Well, it turns out that R value is really sort of the K divided by the L. So if you take the, or actually it's more like the L divided by the K. L over K is essentially equal to the R value. Okay, so you're taking a K for fiberglass and you're taking the length, which is built in. So this one's supposed to be 5.5 inches, for instance. So the L up here would be 5.5 for R19. For here, it would be 3.5. Because the 2x4 is not really 4 inches thick. It's only 3.5 inches, and the 2x6 is not really 6 inches thick. It's 5.5. So that really is what the R value is. So if you look at this equation in terms of R value, you'd say delta Q over delta T is equal to 1 over R times A T2 or T1 minus T2. So that's the difference. And actually by doing that, it actually allows you to combine insulations a little better. So this equation right here is something you need to know how to use. It's pretty straightforward. I think it's one of the simplest equations you can use. You just got to remember that T is time, not temperature. And these T's are temperature. This is area like square meters, square centimeters, and this is length like meters and centimeters. Long as this unit, which is squared, matches this unit, which is not squared, your equations work just fine, okay? Now, the other equation was the Stefan-Boltzmann law, and I want to make sure you know that. And the Stefan-Boltzmann law basically says that radiation, so this one's for radiation. This one was for conduction. This one for radiation says that delta Q over delta T, which in astronomy, we actually call that the luminosity. So in your light bulb, for instance, if you buy a 100-watt light bulb, the luminosity of that light bulb is basically 100 watts. So that's a typical measure of luminosity. It's a little weird though, because the light bulb, 100 watts of energy is being burnt by it, but a very small fraction of that is in the form of energy of light. The rest of it's outside of the visible spectrum. So incandescent bulbs kind of suck that way. Whereas if you get the equivalent of a 100-watt light bulb in fluorescent lights, then it might only burn, say, 13 watts. And that's more realistic. But what we're saying is the Stefan-Boltzmann law says that the heat transferred per unit time is in fact some emissivity constant, which your book is using that epsilon for it, times the Stefan-Boltzmann constant, sigma, times the surface area, times temperature to the fourth. But here's the weird part. Remember, anything that has a temperature other than 0 Kelvin is radiating heat away to things that are colder. So if you say have a temperature of 100 Kelvin, then you are radiating energy out, but at the same time, the surroundings is radiating energy into you. So they often put it as T4 minus 1 minus T2 to the fourth. So you don't really generally have the Stefan-Boltzmann equation unless you have a energy source putting energy in and an energy taking energy out, a temperature taking energy out. So that's why they're saying that. This is really the Stefan-Boltzmann law, even though they normally just have it like that. And that's what, you know, once we figure out how much radiation a star puts out, we know its luminosity. And then if we can use, for instance, the spectra or some other thing to figure out what its temperature is, then we can use that to figure out what its surface area is. And if we assume it's spherical, as many stars are, then we just say 4 pi squared is equal to A, and that allows us to determine the radius of the star. So that's a very handy thing. So just remember, this A is surface area of the emitter. So these equations are all I expect you to be able to use for chapter 19. For chapter 20, I'm just allowing you, I've set up homework for you to look at. Anything you get above a 0 on that will help you just fine. But the second law of thermodynamics in various forms, for instance, your book says the RJE Clausius form, that is that heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. There's all sorts of versions of the second law. So the efficiency of a heat engine is never more efficient than a Carnot engine. No device is possible where the sole side effect is to transform a given amount of heat completely into work. That's another version of the second law of thermodynamics. Basically, if you just read through chapter 20, you'll see a bunch of bold print sentences and paragraph. And for instance, all reversible engines operating between the same two constant temperatures, TH and TL, have the same efficiency. Any irreversible engine operating between the same two fixed temperatures will have efficiency less than this. So that's basically just saying, hey, if you can't, if your engine runs between the same temperatures as a particular Carnot engine is, then your engine is going to be less efficient than the Carnot engine. Another one is no device is possible whose sole effect is to transform a given amount of heat completely into work. That's more or less the same thing that was said a few minutes ago. No device is possible whose sole effect is to transfer heat from one system at a temperature TL into a second system at a higher temperature TH. That's another version. And then entropy gives us yet another way to talk about the second law of thermodynamics, and that basically says the entropy of the universe tends to go up. The entropy of an isolated system never decreases. It either stays constant in a reversible process or increases due to irreversible processes. And the total entropy of any system plus that of its environment increases as a result of any natural process. Here's another version. Natural processes tend to move toward a state of greater disorder. And here's another. In any natural process, some energy becomes unavailable to do useful work. So that's sort of us thinking about energy and heat as different types of energy. Heat is sort of a low quality energy, because once you actually turn energy into heat, basically it's like herding cats. You're distributing a certain amount of calorie to every molecule and atom within the substance. The likelihood that you can get exactly that much radiation or energy back out of those individual molecules is nil. So you're always going to lose some energy when you transfer something from energy to some form of heat and then back. Okay, so those are the various forms of the second law of thermodynamics. I think I've covered more than enough for chapters 19 and 20. Next time we will go into quantum mechanics, which if I remember correctly is like chapter 40 or 41. Let me double check on that real quick. Not 40. 38 and 39. Actually, it might even be 37 and 38, excuse me, because 36 was relativity. 37, I think, is early quantum theory. Yeah, 37 is early quantum theory. So we'll do 37 and 38. That's all we have left for this semester. Anybody have any questions? Everybody, of course, the time is over, so you're free to go, but you're also welcome to stay if you have any more questions. I know I covered stuff in a highbrow way in this last lecture, but it's really is trying to give you the details of the concepts so that you can then apply them. I think if you read the book and then try to do the examples in the book, you'll have no problem translating that and solving other problems like what you have in your homework. So, but if you don't, just let me know.
All righty, have a good night.
You too, Sean. How it going? Anybody else here?
Professor?
Yes.
Did you happen to get my email that I sent you about the integration by parts problem in
Yes.
chapter 18? Okay.
Yeah, it was attached to it. I thought I said got it and that was it. But yeah, I remember getting it. I've got a flag on it, so I'll know to grade it when I have time and give you partial credit or extra credit for it.
Thank you very much. Just wanted to make sure.
Have a good one.
Have a good night. Yep, you too.
Bye-bye.